Welcome. My name is Kyle Waldron. I'm a current board member for SURF, and I'd like to welcome you to today's presentation. SURF, also known as the Sustainable Remediation Forum, is a nonprofit organization, and our mission is to maximize the overall environmental, societal, and environmental benefits of remediation by advancing science and application of sustainable remediation, developing best practices, exchanging professional knowledge, as well as providing education and outreach. Ben, if you want to flip to that first slide. SURF is made up from representatives from site owners, agencies, academia, consultants, specialty vendors, and the public. And for more information on SURF, feel free to reach out to or go to our website. And there's also a great video there from our UK affiliate, SURF UK, that provides a nice overview of the basics of remediation. But there's tons of great information on the website, including what we're doing regarding case studies, publications, all kinds of stuff. So go there and check it out. And if you want to flip to the next slide, Ben. If you miss any part of this webinar or are interested in checking out some of our past webinars, you can go to our YouTube channel as well. And there's recordings from everything we've done to date. And then I'd also like to just give a little info on some upcoming events. So feel free to join us next month at the AEHS conference. We host a number of great talks. SURF has a booth. We also have an open meeting that's available to anyone. So for more information on that, they'll sign up for our emails and you can find it, or also go to the AEHS website. So keep an eye out for all that. But our speaker today, what you're here for, is Ben Alexander from Tri-Hydro. He is a professional geologist based in Maine, and he works on developing and improving site conceptual models, as well as creating remediation and monitoring programs for petroleum release sites. He has a MS in environmental engineering from the University of Wyoming and a BS in environmental sciences and engineering from the University of North Carolina. If you look on the GoToWebinar tool, you can find a number of handouts, including a couple papers, one of his most recent ones on the feasibility of greenhouse gas emission offsets for NSCD, which is the subject of today's talk. So with that, I am excited to welcome our speaker, and Ben, it's all yours.
All right, thank you very much. We are going to be talking about a topic that is under the broad umbrella of green cleanups. Green cleanups for our environmental sites try to, amongst other things, minimize the environmental footprint of our remediation activities. So for our remediation activities, one thing we're trying to minimize is greenhouse gas emissions. And there are several steps in remediation that can lead to those emissions. We may be out drilling and doing investigation, and having those big rigs on site can have CO2 emissions associated with them. If we're installing infrastructure for remediation itself, maybe doing some pumping and then operating those systems, those can have greenhouse gas emissions. Site monitoring, where we're driving trucks around or analyzing samples in a laboratory, or even sitting in our offices and writing reports, each of those steps have emissions, greenhouse gas emissions associated with them. And that's the case for pretty much any contaminated site and any cleanup. But petroleum sites are special in that they have an additional component of emissions to the atmosphere. The LNAPL in the subsurface itself is a petroleum hydrocarbon mixture, and as those hydrocarbons degrade, they can become what eventually are greenhouse gases that are emitted to the atmosphere. So we may have volatile organic compounds that leave the LNAPL in the vadose zone and near the LNAPL body, we tend to have low oxygen conditions, so biodegradation occurs mainly by methanogenesis there. As that methane and the VOCs move upward in the subsurface, they usually contact a zone that's high in oxygen, and then aerobic microorganisms are able to degrade the methane and VOCs and convert them to CO2. So at our petroleum sites, we have mostly CO2 and maybe a little bit of methane coming out of the ground. And this is an additional source of greenhouse gases to the atmosphere. We know about these emissions because from most perspectives, we're happy with them. We want to see CO2 coming out of the ground. And in fact, we quantify it because it helps us have evidence that the LNAPL is degrading and that our remedy is progressing. But from the perspective of green cleanups, we are going to take the perspective in this presentation that those emissions as greenhouse gases are important to be aware of. So that perspective we're going to look at in a couple of ways. One is at the remedial alternatives evaluation part of cleanup. We're going to look at not just the emissions associated with remediation, but also those associated with contaminant biodegradation. And when we add those together, that gets us a better estimate of the full site emissions for greenhouse gases. It also allows us to look at which remedy alternatives are able to decrease those contaminant biodegradation emissions, and that can help us identify what really does look like it would have be the greener cleanup alternative. And then as we'll see, even the greenest cleanup is going to have emissions associated with contaminant biodegradation. And so we'll explore that possibility of using our site, our brownfield, as a way to get credits for offsets of those emissions. So we'll look at each of those parts of the topic for this presentation. We'll start with an example footprint analysis. That's to look at the remediation or the remedial alternatives part of this perspective. We will, a footprint analysis can incorporate a lot of different components. It can look at the water use for remediation at a contaminated site. It can look at materials use, and it can look at greenhouse gas emissions. We're just going to focus on the greenhouse gas emissions for this part of the presentation because that's our focus, is those sorts of gases. But we'll look at a hypothetical petroleum release site. We'll look at 5 remedy alternatives, and we'll look at not just the remediation emissions, but also the contaminant biodegradation emissions for each of those alternatives. And we'll see how do they stack up against each other. Our hypothetical petroleum release site is a moderate size site. It is 30 meters wide by 30 meters long and less than a meter thick LNAPL smear zone. We are going to go ahead and assume that the LNAPL type in the formation is gasoline and that the soil type is a moderately permeable fine sand. So it's a simple site. It's a hypothetical site. If it was a real site, it would not have a uniform soil type. It probably wouldn't have a uniform NAPL type, and it almost certainly would not have a uniform smear zone thickness, this 0.8 meter thick smear zone. But for the purposes of this little exercise here, we have a nice simple site. Because the site is so simple, we actually do have enough information to estimate how much LNAPL is in the subsurface. We can plug in this information here to the API LNAPL distribution and recovery model. This is freely available online, and it allows you to plug in input parameters about your NAPL type, your soil type, and your smear zone thickness to generate an LNAPL saturation profile for that vertical interval of the smear zone. And with that, when you have that as a vertical profile, you can multiply that times your footprint and you have a NAPL volume. So when we do that, for this exercise, we come up with a NAPL volume in the formation of 100,000 liters. If we have an estimate of the residual NAPL saturation in the formation, then we also have sufficient information to estimate the recoverable fraction of NAPL in the subsurface. And as is typical for NAPL sites, the majority of the NAPL is not recoverable, and it comes out as 40,000 liters that would be recoverable at this site. Since we know how much NAPL is in the subsurface and we know the NAPL type, we can also say stoichiometrically, if all that NAPL were to degrade, how much emissions will we have as CO2? When we do that exercise, it comes out to about 250 metric tons of carbon dioxide. As I mentioned, generally at our LNAPL sites, we don't have much methane coming out of the ground. And so for the purposes of this exercise, we just assumed that about 1% of the emissions are as methane. That comes out to about 2 metric tons of methane. Methane has a higher global warming potential than CO2. So that comes out to about 40 metric tons CO2 equivalent for the methane. So this 250 plus 40, so about 290 metric tons of CO2 equivalent is how much greenhouse gases would be emitted to the atmosphere if no remediation were done at all. So now we're going to look at 5 different remedy alternatives and look at the remediation emissions and the contaminant biodegradation emissions and see for that total, what's the difference for each of those remedy alternatives. For the remediation emissions, we use the site-wise software that is also freely available online. This is a software that is a footprint software for remediation. And so it'll give you things, outputs that are things like water use and equipment use and greenhouse gas emissions. And so we use just the greenhouse gas emissions part of it. And for this part of the exercise, I'm saying we did this because my co-worker, Kurt Tuggle, and I went through this exercise together. For each of our remedy alternatives, we are going to assume the same amount of monitoring is conducted for each alternative. 10 years of groundwater sampling, that's quarterly sampling for the first 5 years, and then annual sampling for the next 5 years. So we can plug in those efforts into the site-wise software and get a footprint estimate just for the monitoring part. Our first remedy alternative is excavation. Oftentimes for alternatives evaluations, we have one end of the spectrum that is the highest level of effort and then another end that is a lower level of effort. Excavation is often at the highest end of effort. So we plugged into SiteWise, putting lots of big rigs onto the site, big equipment onto the site to dig up those soils. It is an LNAPL site, so LNAPL is at the water table, and so we also incorporated dewatering that water table so that we can really get to the LNAPL impacted soils and dig them up. And then we added into the site-wide software transport of those soils offsite to a landfill. So those are all the pieces that we can plug into the site-wise software and get the remediation emissions for. For the contaminant biodegradation emissions, we went ahead and assumed that this landfill that we're shipping our soils to is just doesn't have any special gas capture equipment on it. And so we do not have a change to the contaminant biodegradation emissions for the excavation scenario. Whether the LNAPL is at our site in the subsurface or it's at a landfill, it's still going to degrade eventually and be emitted to the atmosphere as greenhouse gases. Our next 2 remedy alternatives are related to LNAPL recovery. Both of them use the same effort for recovering LNAPL. They have 11 wells and they operate for 10 years. And they pump that NAPL out of the ground. Technically, as you would see, if you were to plug this information about the site characteristics into the LDRM software, that NAPL recovery software, what you would see is that most of the NAPL would be recovered in the first 2 years of operations. But for the purpose of trying to be more realistic about how long NAPL recovery systems usually are operated, we went ahead and said that we would do it for 10 years. And What that really means is that after we get that first big pile of NAPL out of the ground that's easy to get, we do a lot of water extraction, try to create a cone of depression, and induce NAPL flow to the well to get the last bit of NAPL out for basically the next 8 years of remediation. So those are the remediation operations that you can plug into the site-wide software. For one of our LNAPL recovery scenarios, we went ahead and said that we're going to recovered product is going to be transported off-site and it's not going to be recycled. And in that scenario, that does not change the contaminant biodegradation emissions. Whether that NAPL is at our site underground or it's somewhere else, it's eventually going to be emitted as a greenhouse gas by biodegradation. For our other NAPL recovery scenario, we went ahead and said that we will recycle our product that's recovered. And so in that case, we have LNAPL that doesn't biodegrade that's recovered. Instead, it's put to a beneficial reuse. Maybe it's sent to an operating refinery and put into the process stream, or maybe it's sent to an industrial plant and it's used for purposes to run the plant. In that case, the LNAPL, it doesn't directly biodegrade and it's put to a beneficial reuse. And so we count that as a credit against the contaminant biodegradation emissions. Technically, that LNAPL still is emitted as a greenhouse gas. When you burn it, that gasoline, it will be emitted to the atmosphere. But because that gasoline that we do burn, that is product that was recycled, that displaces gasoline that otherwise would be burned, then we do count it as a credit against the contaminant biodegradation that occurs at our site. So that's for the NAPL recovery option. Our next remedy alternative is passive bioventing. This is typically considered to be a green remedy alternative. We went ahead and plugged into the site-wide software, putting in 10 biovent wells, and we plugged in analogies to the software of what's shown on this top little picture here, where you can have a little wind vane and a funnel to hopefully get more air into the subsurface for your bioventing well. So we plugged in that sort of infrastructure into site-wise. You could get a lot more air into the subsurface. We are currently doing air sparging at a site in Wyoming, as shown on this lower picture here, with wind turbines. And so with that approach, you can get a lot of air into the subsurface. It's air sparging in that case, but you could do it as bioventing also. But for the purposes of this exercise and the site-wide software, we just assume the infrastructure that's shown on the top picture. Putting all that air into the subsurface should mean that any methane that's trying to get out of the ground, maybe when it's wet out and there's not a lot of oxygen going into the subsurface, that methane is going to get converted to CO2 because we have so much air in the subsurface. So that does decrease the contaminant biodegradation emissions. And finally, our last remedy alternative is monitor natural attenuation. This is where we only monitor, we have no additional remediation, and this does not decrease the contaminant biodegradation emissions. At best, it only tracks them. So how does it turn out? What is the total emissions that we have for each of these remedy alternatives? The first graph we'll look at is the remediation emissions. This is the part that is the output from the site-wide software. And what we see is that LNAPL recovery without product recycling and with product recycling, the remediation emissions for those alternatives are the highest of all of our alternatives. They are higher than excavation. Excavation has high emissions. It has 80 metric tons of CO2 equivalent, but LNAPL recovery comes out way ahead of that. And the reason is that we went ahead and said that we're going to do LNAPL recovery for 10 years. So you can see on this lower part of the graph that the orange box is for equipment use and miscellaneous. That is the big part of the emissions associated with the LNAPL recovery option. And that's basically O&M for 10 years of a NAPL recovery system that has water extraction and water separation with it. So when we went through this exercise, one thing that we saw was that, okay, this would emphasize why you would try to have good recovery endpoints for a system so that you can minimize how long you're operating it. If it just takes 2 years to get most of the NAPL out of the subsurface, then it could make sense that that could be the time frame for remedial operations instead of 10 years or even longer, which is often typical. As I mentioned, excavation does have high emissions associated with it. M&A comes out, of course, as the lowest emissions for remediation. It is, of course, the lowest because the same monitoring that's in M&A was incorporated to the other alternatives. So M&A doesn't have any other actions, and so it's going to have the lowest remediation emissions. Passive bioventing has relatively low emissions, but they are higher than M&A because of that extra effort we're doing to get the infrastructure into the ground. So that's the remediation emissions. That's where a typical footprint analysis for greenhouse gas emissions would stop, but we're not going to stop there. We're also going to look at the contaminant biodegradation emissions. So what we see is that excavation, LNAPL recovery without product recycling, and M&A, they come out as having the highest emissions. They come out as having the same emissions as if you weren't doing remediation at all. We have mostly CO2 emissions, which is the purple bar, and then we have additional emissions as methane. LNAPL recovery with product recycling, that ends up having lower emissions than the other alternatives for contaminant biodegradation. And that's because about a third of the NAPL that's in the subsurface is put to a beneficial reuse, and we count that as a credit. So that gets a decrease in the contaminant biodegradation emissions. Passive bioventing also has a decrease in emissions. We convert that pink methane to a little bit of extra purple CO2. And so overall, it means lower emissions for bioventing than for if nothing was done. So that's remediation and contaminant biodegradation. What happens when we add them together and we get a total greenhouse gas emissions for each alternative? It turns out like this. We have contaminant biodegradation as the dark green bar and remediation emissions as the light green bar. And the way it turns out, the first thing that we see when we look at this graph is that contaminant biodegradation is significant in all cases. So if we're not counting that as part of the footprint, then perhaps we are missing something. The alternative that has the highest total greenhouse gas emissions is LNAPL recovery without product recycling. You basically have the worst of both worlds. You have no change in the contaminant biodegradation emissions, and then you have all those remediation emissions from operating your system for so long. LNAPL recovery with product recycling has lower emissions, and it's actually a little bit lower than excavation. It's basically competitive with excavation. So we get that great credit from recycling our product, and but we also have those relatively high remediation emissions. And so that again emphasizes that, for comparing that with excavation, we're still only competitive with it, and operating that system for so long means high emissions. M&A does not come out as the lowest total greenhouse gas emissions of our alternatives. That honor goes to passive bioventing. Even though M&A has relatively low remediation emissions compared to passive bioventing gets a credit for converting that methane to CO2. And so overall, it comes out ahead of M&A. And so when we went through this exercise, what it said to us was that, a lot of times when people hear green cleanup, they think, oh, you are trying to do as little remediation as possible. You're going to do M&A. That's what you think is the greenest cleanup. Well, not always. In this case, when we incorporate the total emissions for greenhouse gases for these alternatives that include biodegradation, it actually turns out that M&A does not win. And if we are only looking at greenhouse gas emissions as our criteria for remedy selection, we might actually pick passive bioventing. It comes out as the winner. So green remediation, when we think about that, it often does mean doing remediation, active remediation. In this case, it means using natural processes to help speed up your remedial activities. Of course, greenhouse gas emissions are not the only thing you think about when you're doing an alternatives evaluation. And really, in reality, what you might do in this case is you might do LNAPL recovery early. Maybe you try to get your remedy time frame down to just those first couple of years, and then you could transition to passive bioventing. But generally, what we can see is that M&A doesn't win in this case. That distinction goes to passive bioventing. So that is the end of the first part of our presentation. We looked at doing a footprint analysis for remediation of a hypothetical petroleum site, and looked at not just the remediation emissions, but also the contaminant biodegradation emissions, and hopefully made the case that if you don't look at contaminant biodegradation as part of the total, then you may be missing something. In our case, it helped us to see what alternatives can decrease the emissions associated with contaminant biodegradation. It showed us that bioventing wins over the other alternatives, and that LNAPL recovery with product recycling becomes competitive with excavation and could be even more competitive if the time frame was lower. So that's the first part of our presentation about remedy alternatives evaluation from this perspective that we're taking. Now we're going to look at the implications of this part of the graph here that we looked at a moment ago, where contaminant respiration, even in the case of passive bioventing, the alternative that wins, contaminant respiration or biodegradation is a significant part of the emissions that are going to occur at a site. And what can we do about that? Some of those emissions are going to be unavoidable. Even our greenest alternative has emissions. So the idea we're going to explore next is, can we use the site itself to offset those emissions of LNAPL degradation? The idea is that we have, just like we talked about a minute ago, when we're doing all the remediation, we have all these emissions associated with our activities. And even after we're done with all that remediation, we're probably going to have a late stage LNAPL site. Maybe we're just managing the residual LNAPL in place. And all that time, we will have emissions that are occurring due to biodegradation of the LNAPL. Like I said, for the most part, we're happy with those emissions. We may actually be counting them to have a feel for how fast is our LNAPL source degrading. So from most perspectives, we're happy with it, but it is an emission source to the atmosphere. And the question we're going to look at now is, can we use our site to offset the amount of emissions that we have from LNAPL biodegradation? For instance, could we put solar panels across our site footprint and have those solar panels remove enough CO2 from the atmosphere to match the amount of emissions we have at our site? So we'll look at that for solar panels. We'll look at other site reuse options. And of course, solar panels don't actually suck CO2 out of the atmosphere. They displace energy sources from the grid that have relatively high greenhouse gas emissions. So we have lower emissions to the atmosphere by energy generation than would have occurred otherwise. And we're going to see if that can provide an offset to our contaminant biodegradation emissions. To do that, we have to have a feel for what kind of emissions can we expect for our sites. And the natural source zone depletion, or NSED field, looks at that question. I went ahead and compiled a literature review here. These are what I feel like are the best studies that are out there about NSED rates that are in the field. I may be biased. I'm an author on a couple of the studies, but I feel like this is a good compendium of rates that you can expect. We have the former Guadalupe oil field that is maybe the most famous NSED site. We have a couple of former refineries. We have the Bemidji site in Minnesota that has been so extensively studied by the USGS. And we have a really good study by Doug McKay at UC Davis for a former service station in Southern California. So these are what I feel like are good studies, and the NSED rates that we have for those sites, these are all late stage LNAPL sites, are generally in the range of 0.5 to 4.5 or 4 or so micromoles CO2 per meter squared per second. So that is about the range we can expect. On the graphs I'm going to show you next, where we're looking at offsets, I went ahead and pushed the graphs all the way up to 10 micromoles CO2 per meter squared per second, just to be safe for possibly higher rates. But for the most part, we can expect to be in the 0.5 to about 4 micromoles CO2 per square meter per second range. There are atypical sites out there with higher rates. There's a site where higher rates were measured at a recent release in Minnesota. And so that probably can't be expected that that higher rate to persist into the future as the LNAPL degrades. There are ethanol sites out there that have considerably higher emissions rates, and they even have quite a bit of methane coming out of the ground in some cases. Methane is especially edible to microorganisms, and so you can really get a lot of gas generation. But again, because the ethanol is so edible, it's probably not going to be an emissions rate that you can expect for as long as you can for a late stage petroleum site. So the 0.5 to 4 range does seem about right for what we'll be looking at next. So that's our emissions rate we can expect for our sites. Now, when we look at renewable energy, what we need is an amount of CO2 equivalent that's removed from the atmosphere per kilowatt hour of energy produced. A really good source for that information is this graph here that I'm showing. This is a compendium of about 950 life cycle analyses that were done for multiple energy sources that was generated by the IPCC. They did this work. So for each energy source, it is a distribution of CO2 equivalent offsets per kilowatt hour, or CO2 equivalent generation per kilowatt hour that includes a maximum, a minimum, and a median. So for our purposes, we will go ahead and just use the median values. And so we'll look at solar power and wind energy. In the case of photovoltaics, we have about 40 grams CO2 equivalent per kilowatt hour that are emitted to the atmosphere by this energy source. And so we're going to say that that displaces another energy source from the grid when we place it at our site. For this exercise, I went ahead and just picked natural gas as the energy source that's being displaced from the grid. It's a middle of the road energy source from a greenhouse gas emissions perspective. So if you subtract the median for photovoltaics from the median for natural gas, it comes out to about 430 grams CO2 equivalent per kilowatt hour that are offset when you go with photovoltaics. Wind energy is also on this graph, and it has such a small emissions rate that you can barely see the median black line on this graph. And so when you subtract wind energy from natural gas, it comes out to about 470 grams CO2 equivalent per kilowatt hour. So we can take those unit rates and other information, engineering information about those renewable energy sources and plug it into graphs like what we have here. On the x-axis, we have contaminant soil respiration emissions rate. So this is that NSED rate that we were talking about, up to 10 micromoles CO2 per square meter per second. On the y-axis, this top graph is for solar power. We have the photovoltaics footprint versus the site footprint. So if you were at 100% on this graph, then all of your site would be filled up with solar panels. And then we have different lines for the type of solar resource that you have, or the magnitude of the solar resource. And so the 2 kilowatt hours per square meter per day would be for a relatively not sunny place, maybe like southern Alaska. And then 8 kilowatt hours per square meter per day would be a very sunny place, like maybe the desert Southwest. And what we see on this graph is that even for the low solar resource, we never even get up to 40% of our site being used for solar panels to get a full emissions offset. And that's at the highest NSED rate. It's really outside of the range that is typical. So this assessment suggests that you could get an offset of your contaminant related emissions at your site with solar panels without using up your whole site. And if we're in the 0.5 to 4 range on this graph, then we're using less than 20% of our site. So you have room for other things that you can do with your brownfield reuse. For wind energy, what we have is wind turbine swept area as what's on our y-axis versus the NSED rate. And we have a relatively low wind resource, 4 meters per second. That's like in the southeastern US versus 10 meters per second. That'd be like a really windy place. And what we see is that for the lowest wind resource, we end up with a maximum wind turbine swept area of about 400 square meters. That's a big wind turbine. That corresponds to about a 150 kilowatt wind turbine. That is big. It's not as big as the utility scale wind turbines that are being built today. You know, they're measured instead of this 150 kilowatts, more like megawatts for utility scale. So it's a big turbine, but it's not utility scale turbine. That's at the poorest wind resource and at a really high NSED rate. For other wind resources and the more typical NSED rates, we're at 50 square meters or less for wind turbine swept area. That is getting to be about a 10 kilowatt wind turbine, and that's becoming a very reasonably sized turbine to operate at a site. So this little analysis here suggests that you could get an offset for your contaminant biodegradation emissions at your petroleum site by putting out a wind turbine, or you could use solar power. So that is renewable energy. Another way that you can reuse a site is to have revegetation. People do revegetation at brownfields for multiple reasons. Maybe they want to make it pretty as a nice green space. Maybe they want to put it to a beneficial reuse that involves vegetation. Maybe they're doing phytoremediation. So there are reasons that people do revegetation at brownfield sites, and that vegetation can sequester organic carbon that comes from the atmosphere. So it can take CO2 out of the atmosphere, and it can store organic carbon above ground in the plant material, or it can store it below ground in the soil organic matter associated with those plants. To get a feel for what kind of an offset can you achieve with that type of site reuse, there's a good resource out there. The USDA in 2003 put out this document that's shown on the slide, and it has carbon stocks for both above and below ground for different forest types. So I selected 4 forest types to get a range, and they correspond with different geographic areas of the US. We have elm ash cottonwood in the northern prairie with about 100 metric tons carbon per hectare that are sequestered, up to, in the southeast, the oak gum cypress forests, which has about 186 metric tons of carbon per hectare. So we can plug in these different unit rates to see what kind of an offset we can achieve with trees. Revegetation doesn't have to be trees. It can also be converting your site to rangeland or cropland or maybe even wetlands. And there you don't really store carbon above ground. It's mostly stored as soil organic matter below ground. And the values that we have for those types of revegetation scenarios go from 40 metric tons of carbon per hectare up to 260 metric tons of carbon per hectare for a wetland. So we can plug in those unit rates to our graphs and see how it turns out. And what we get is, on this top graph, we have the forest. We have the forest footprint versus the site footprint. So if you're at 100% on this graph, your site is all trees. And you may remember from our renewable energy graphs that we had relatively flat lines. They're much steeper in the plant regrowth graph here, this forest graph. We get up to 100% of our site at 1 or 2 micromoles CO2 equivalent per square meter per second. So we don't as easily get to an offset with plant regrowth. It does look like it is viable to get an offset by using a large proportion of your site if you have a relatively low NSED rate. But it looks like, at least for this exercise, you may not get a full offset if you have relatively high NSED rates, even if you use up your entire site for forest growth. For those soil organic matter options, the rangeland and cropland and wetland scenarios, it's a similar story. We have relatively steep lines here. And so basically you really need to know what your NSED rate is at your site to see if you can get an offset by using a large proportion of your site, probably for reuse as revegetation. Wetland does fare better than the other revegetation options. It sequesters so much organic matter in the soil, but I would caution against using this graph straight up to say that an offset is achieved. While wetlands do store a lot of organic carbon in soil, they also have waterlogged conditions, and so you can have methane emissions and nitrous oxide emissions associated with wetlands. So it's not a given that you could get that offset that you're searching for. So that is plant regrowth. Our final method that we'll look at for achieving an offset is spreading calcium-rich construction materials at our site. This last method is based on some really interesting research that has been done that I found in the literature that's mostly been done in the UK. You can see one article here with the authors. And the idea is that when we have construction when we build buildings in the world, that involves a lot of times taking carbonate materials, calcium carbonates like limestone, and mixing them with clays and sands to create cement. And then you get reactions that give you calcium silicates, artificial calcium silicates, and those are great for building things, cements and concretes. That has emissions associated with it. Cement plants are a significant contributor of greenhouse gases to the atmosphere, as those carbonates become CO2 that go to the atmosphere. It turns out that that method or that reaction is reversible, that you can have CO2 re-enter those materials and convert back to calcium carbonate. That occurs when those construction materials, instead of being big blocks, are broken into very fine powders, and then you can have CO2 taken up by those materials. So the idea is to spread those calcium-rich construction materials across land surface and have the CO2 get pulled out of the atmosphere with them. These researchers have obtained unit offsets that are similar to what we looked at for those carbon stocks for revegetation, and the numbers are big. They come out to about 1,000 to 1,800 metric tons of carbon sequestered per hectare. And for those revegetation options, we were looking at values like 150, maybe 200 metric tons carbon per hectare. We're at 1,000 to 1,800 here, so it's a lot. So if we plug those numbers into our graphs, we get, even at the highest end of our emissions rates, we are not using the entire footprint of our site. And especially if we're in the more realistic range that we're used to seeing for emissions rates, we're not even using 40% of our site. So this may be a way to get that offset if you're looking for it. And it's attractive because you can see in the title of this article, rapid removal of atmospheric CO2, as opposed to having sort of plants that take a long time to grow, or solar power that you have to operate for years and years. Maybe it's just a few years where you spread these materials out at your site, suck up that CO2, and then you have time in the future for additional reuses. Maybe you want to put buildings at your brownfield, and you can just use those spent construction materials as part of grade. Maybe you can just leave them there. So this could have a use, especially in urban settings where you have other plans for your site. So that takes us to the end of this perspective that we are considering for this webinar. And that perspective is that those greenhouse gas emissions associated with NSED, we like them in a lot of ways. They help us show that we're getting remediation. But if we are taking a complete look and thinking from the perspective of green cleanups, we should count them. And in pretty much any case, there are unavoidable emissions associated with contaminant biodegradation. It does look like with these different methods that it is possible to achieve an offset. You can do renewable energy, you can spread those calcium-rich construction materials, you can even do reforestation or revegetation in the right emissions rates scenarios. So that takes our topic to its end. This presentation will be available at the SURF website, and it has references in it that are that we looked at in this talk. This talk is based on 3 articles that I wrote, and one that I wrote with my co-author Kurt Tuggle. Those are also available on the SURF website, and so you can use those to see if this idea has merit for your own site and maybe put it to use.
Okay, thanks, Ben. Now we'll go ahead and take some questions. Feel free to input those into the questions box as part of the slides here, and we'll get to them as we can. First question today is, when would you account for methanogenesis in your greenhouse gas emissions estimates?
Okay, so I think you're talking about methanogenesis of petroleum hydrocarbons, and that occurs, let's go back to our little figure here. Methanogenesis occurs almost exclusively, let's go back here. Methanogenesis excludes, I shouldn't say almost exclusively, below the water table we have other biodegradation processes like anaerobic sulfate reduction and nitrate reduction, and methanogenesis. But methanogenesis is a big part of contaminant biodegradation. And so if that methane is emitted to the atmosphere, then it would count as a really big emission source to the atmosphere, and then you would account for it. I will say that the experience that's out there is that for the most part, we don't have much methane that leaves the ground surface. It's mostly carbon dioxide, and that's because we generally have good aerobic conditions somewhere in the vadose zone. It may be only at 3 feet below ground surface, but generally we do have good aerobic conditions to get that methane converted to CO2. I've gone looking for the methane like others have at late stage sites, and even when I have had waterlogged conditions and I'm getting high CO2 fluxes because the soil is slowly drying out and then all of those gases are being released, even then, I haven't really seen many methane emissions. They're just not that prevalent. I have detected them, they do occur, but at a petroleum site, they just aren't that significant. And it's fair to assume that they are only a small component of the total emissions to the atmosphere.
Okay, yeah, thanks. Next question, how is time incorporated into the assessment? The impact of emissions over a short period of time versus a longer period of time would assumably have different impacts.
Right. Well, from the perspective of remediation emissions, well, I should start with, for all of these assessments, they take the simple view that any greenhouse gas in the atmosphere, whether it's emitted today in one burst or over the course, or a slow burst over the course of 10 years or even 25 years, is the same. That's a simplistic way to look at it, but it did allow for easier comparison between these different ways of looking at the topic. Time was something that we did have to think about a lot, partly for the remedial alternatives assessment. I'm not sure that we did it exactly the right way. We went ahead and said that we have a 10-year remedial time frame for every remedy alternative, when in reality, you may have, like we were talking about earlier, if you can transition out of LNAPL recovery early, then maybe you can get to bioventing relatively soon. And especially if you're thinking about, oh, well, let's just do bioventing as the only remedy alternative. Well, this was a site with 30% recoverable NAPL. You're not going to be doing bioventing probably as the only remedy alternative. You're probably going to be doing it after LNAPL recovery. We put all of those remedy alternatives on the same playing field of 10 years. But I think that when you get to the site-specific approach, you really would start thinking about, well, how long am I going to operate a system? And a more effective system in a short time, you would want to get credit for that. So that's one part of it. The other part of it is when you think about offsets, the way that we incorporated time was for renewable energy. We just went ahead and tried to get the offset to match the offset per year to match that occurs per year by NSED. So there had to be some sort of engineering thinking there. But I tried to make it realistic for you by instead of saying what's the total emissions you'll have for a site over its entire time frame, we tried to give you an NSED rate of micromoles CO2 per square meter per second. That's something you could pick your time frame for and align to your offset option.
Have you ever been asked to report these greenhouse gas emissions from remediation sites that are included in a company's sustainability report?
I have not done a lot of work on this topic that isn't hypothetical. I have done some work to employ green remediation, and I think that we're making a difference with that. But as I think the green remediation field points out, that there are different levels for an assessment of your green remediation. You could do a greenhouse, you could do a footprint analysis, you could do simple best management practices. And so in my actual project experience, I have not employed a lot of the I haven't taken it to the level of a footprint analysis that we're looking at here for most sites. So a lot of this is trying to get the information out to others that do it more often. So hopefully you can incorporate some of this thinking to your assessments.
Okay. A question kind of related to the literature that's out there. What assumptions were made to model the calcium-rich construction materials being distributed to the site? Was it mixed into the soil a foot deep, deeper? And like, do they take into account the greenhouse gas emissions from crushing that material and transporting it, or is that a separate?
Yes, that's a good question in that all I did, so as far as the implementation part, I can say that it is the materials are not mixed in with soil. They're actually used, you want to maximize your exposure, your surface area to the atmosphere. So they are treated like soil as soil cover. And then they're in, you'll be able to see in the list of references, so that'll be the Washburn article here, and then the Renforth article here. You'll be able to see some graphs of the CO2 uptake that was achieved. And there's at least one graph that shows that I think maybe they did, I don't know, a meter thick soil cover. I don't remember the thickness exactly, but most of the CO2 was taken up in the top few feet, I think, and then things drop off from there. So if you were to proceed with this approach for your site, you would be able to use those materials to get a feel for what kind of thickness is optimal for your site. And then you would want to incorporate that into, well, could I still build on that and try to fit it into your longer term plans? As far as the true offset, I don't think that there's any well, I'm pretty confident there was no incorporation of what's the life cycle of this approach. I think it really is just an offset for those materials, you know, how much carbonate was formed basically. So I guess you could do a discount for, well, you have to actually get those construction materials to your site, you have to break them up. And so you maybe could incorporate that to discount it some. But that graph shows that you have a lot of the material does so well versus, you know, what our NSED rate that even if you did discount that, I think you're still going to win and get your offset.
Okay, well, looks like we're pretty much wrapped up with the questions, unless anybody else has any more. So I think we'll pass it on to Kyle to close us out here.
Yeah, we want to thank Ben for a great presentation. I thought it was a lot of great information. And a special thank you to our sponsors for SURF. They allow us to do these types of things. And lastly, big thanks to TriHydro for hosting this webinar platform for us. So look forward to hopefully seeing some of you at AEHS. And if not, look for the next SURF webinar to come out probably late fourth quarter. All right, appreciate you guys. Have a good day. Bye.